Welcome back, grade 10s. In today's lesson, we will continue to learn about electromagnetic radiation. We're going to start off this lesson by discussing each type of electromagnetic radiation, starting with the lowest energy wave, the radio wave, and moving on to the highest energy wave, the gamma wave. We're going to discuss each one of them in terms of what they're used for. And you definitely need to know a couple of examples of the uses of each type of electromagnetic radiation. So let's start off with radio waves. Radio waves are a type of electromagnetic radiation that has the longest wavelength and the lowest frequency. I'm going to say this over and over again, but remember that when you have a high wavelength, you have a low frequency because wavelength and frequency are inversely proportional. So that means that if the distance from crest to crest is high, there is a low frequency because we have fewer cycles passing a certain point in 1 second. And the other thing that we need to know is that frequency and energy are directly proportional. So a wave that has low frequency also has low energy. Radio waves are used in radio broadcasting, in TV signals, and in satellite communications. The way it works is that a radio transmitter would generate radio waves. Then these radio waves travel through air or through space, and the receiver will pick up the radio waves through antennae. When the radio waves reach the antennae, they induce a current in the circuit of the antenna. The receiver circuit decodes the signal, it extracts information from that signal, and then it creates audio, meaning sound for radio, or data for wireless communication, or audio and visual for TV signals. The frequency of the wave will determine the channel on which it will be received. So there'll be lots of different radio wave signals based on their different frequencies, and a different signal would then apply to a different channel on the TV or on the radio. Radio waves are also used in radar technology, which stands for radio detection and ranging. And that's used in air traffic control, in speed cameras, in weather tracking, and for militaries to detect things like incoming missiles. This is a very similar kind of technology to the sonar technology that we learnt about when we learned about sound waves. But sonar technology uses sound waves, whereas radar technology uses light waves. So radar works by sending out radio waves and then measuring the time that it takes to bounce back after hitting the object. This is very similar to what we learned about the sonar technology. And this helps to determine the location, the distance, the speed of the object. So, for example, air traffic controllers will use radar technology to track planes. The military will use it to track missiles. It's also used in speeding cameras to measure if a vehicle is speeding. And it's used by meteorologists to track weather patterns and to make predictions about weather patterns. Radio waves are also used in wireless technology, in Wi-Fi and Bluetooth, cordless phones, baby monitors, garage remote controls, and gate remote controls. The wireless technology uses radio waves from a transmitter to a receiver. So the signals are created in the transmitter and they travel through space towards the receiver. And that enables communication and control over short distances. So we can use it in everyday applications like Wi-Fi in our homes, like cordless phones in our homes, remote controls for the gate, etc. Let's now talk about microwaves. Microwaves are a type of electromagnetic radiation. They have slightly shorter wavelengths and higher frequencies than radio waves. Microwaves are used obviously in microwave ovens. Microwave ovens, again, contain a transmitter, and the transmitter generates the microwaves. The microwaves, they cause polar molecules like water. Next year, we will learn in grade 11 about polar molecules. But they specifically cause polar molecules like water to vibrate. The vibrations create friction, and the friction generates heat, and it's that heat that then cooks or heats up the food. Microwaves are also used in communication technology. So microwaves are used in mobile phones, in your home Wi-Fi, in satellite communications, and in GPS technology. And the way it works, for example, in a mobile phone, is that it sends and receives microwave signals to and from the router and to and from nearby cell phone towers. Wi-Fi networks use microwave frequencies, and they transmit data between devices using these microwave frequencies that travel through the air. And microwaves allow for fast and efficient wireless communication within a specific range, and that allows us internet access. The way satellite communication works with microwaves is that satellites pick up data relayed from a transmitter on the ground, and then they send it to the consumer. And the reason that we can use microwaves for this is because microwaves can travel large distances through the atmosphere with minimal interference from things like cloud cover, for example, or rain. Microwave radiation is also used in radar technology in the same way that radio waves are used in radar technology. Microwaves are also used in diathermy medical treatment. And what that means is that this little machine will use microwave radiation to generate heat in tissues, and that would relieve muscle pain and it would improve circulation. Infrared is a type of electromagnetic radiation that has longer wavelengths than visible light, but shorter wavelengths than microwaves. It's often associated with heat because infrared radiation is always emitted by objects based on their temperature. So when you're feeling heat coming off something, you are feeling infrared radiation. All objects emit infrared radiation, and the hotter the object is, the more infrared radiation it emits. And that's why infrared waves are also called heat waves. Now, remember that because this is part of the electromagnetic spectrum, it has a color associated with it, but we can't see it. We are blind to that color, so we can feel the heat, but we can't see the heat. The energy carried by these waves, by infrared radiation, is absorbed by other objects and it causes them to warm up. So when you feel the warmth of sunlight or heat from a stove, what you're experiencing is infrared radiation that is being absorbed by your clothes or by your skin, and it is being converted into heat energy. We use infrared radiation in thermal imaging. So we use special infrared cameras that are able to detect heat emitted by objects, and that can create images based on temperature differences. Now, what we need to understand is that when we look at these pictures over here, we're not actually seeing infrared radiation because we are blind to infrared radiation. However, infrared cameras are able to detect the infrared radiation, and then they convert it on a screen into visible light that our eyes and our brains can process. Thermal imaging is used in many fields. So, for example, in medical applications, doctors are able to detect infection or inflammation using thermal imaging, using infrared radiation. Security and surveillance is able to use thermal imaging with infrared radiation to monitor areas at night. And firefighters who would, under normal circumstances, not be able to see visible light through heavy smoke, are able to navigate smoke-filled environments using infrared radiation. Infrared telescopes help us to detect heat from distant celestial objects. Celestial objects are large planetary bodies like stars and planets and moons, and that allows astronomers to study the universe in different wavelengths, not just in visible light. Infrared radiation is also used in remote controls for TVs, for air conditioners, and for sound systems. So the remote sends an infrared signal, which is then picked up by a sensor on the device, and that allows users to control the device over a short distance without physical contact. Infrared radiation is also used in infrared thermometers. Infrared thermometers are able to measure the temperature of an object from a distance because they can detect the infrared radiation or the heat that's being emitted by the object, and then it converts it into a temperature reading. So this is very convenient for temperature measurements without direct contact. Infrared ovens are a special type of oven, just like a microwave oven is a special type of oven that uses microwave radiation. An infrared oven uses infrared radiation. Now, usually these infrared ovens are used in industrial applications. We don't generally use them in our day-to-day lives, in our kitchens, but they use a cooking technology that heats food more efficiently than our conventional ovens because the infrared radiation directly heats up the food, and that results in the food cooking faster and in a more even temperature distribution of the food. We also use infrared radiation in weather forecasting. So satellites that are up in space are equipped with infrared sensors, and they're able to capture the heat patterns in the atmosphere of the Earth. And meteorologists use these heat patterns to track cloud cover, to measure sea surface temperature, to monitor weather phenomena like storms and hurricanes. And this technology is crucial for meteorologists to undertake their weather predictions. Very interestingly, there are some animals that can see infrared light. This is again not visible to the human eye, but it is still being emitted by objects and we're blind to it, but some animals can see it. So, for example, many species of snakes have these specialized infrared sensors located on their heads, and we can see here the sensors being pointed to by arrows, and that allows snakes to detect the body heat of their prey even at night when it's dark. So they would see a mouse or a rat scuttling in the bushes. Vampire bats are also able to detect the body heat of their prey using infrared sensors that they have on their faces, and that helps them find the blood vessels of their prey because it is the blood vessels where the blood's traveling and heat is being released from their prey. Some species of fish, like salmon and trout, can detect infrared radiation. They have specialized cells in their eyes, and that helps them to navigate murky water. So, using visible light, we can't see very well through murky water, but using infrared, these species can actually see quite clearly in murky water. In a similar way to the way that the firefighter wouldn't be able to see through smoke using visible light, but would be able to see through smoke using infrared. And finally, bees and some birds use infrared sensing indirectly for navigation and to locate flowers. So they don't actually have infrared sensors on their bodies, but they have temperature sensors that allow them to detect heat patterns. The next type of radiation is visible light, and that is the type of electromagnetic radiation that can be detected by the human eye. And as we already mentioned in the last lesson, is that it ranges in wavelength from about 700 to 400 nanometers. 700 nanometers corresponds to red light. Red light is the lowest energy visible light wave. To 400 nanometers, that corresponds to violet light. Violet light is the highest energy visible light wave. This range of wavelengths within the visible light spectrum is responsible for the colors that we see, and those are the colors of the rainbow, represented as Roig-Biv: red, orange, yellow, green, blue, indigo, violet. And each color has a particular wavelength or particular range of wavelengths. Human vision and the vision of most animals depends on the visible light spectrum. We have photoreceptor cells in the retina. Humans have rods and cones, and they absorb the light. They send signals to the brain, and the brain interprets those signals as images. Visible light is key to the process of photosynthesis. Who photosynthesizes? Well, plants photosynthesize, and some protists like algae and seaweed photosynthesize, and some bacteria are photosynthetic bacteria. And all of those species contain a pigment called chlorophyll. And that chlorophyll is responsible for capturing visible light and allowing the process of photosynthesis within the cells of those living things. Now, for the process of photosynthesis, it is mostly the blue and red wavelengths of light that are absorbed by chlorophyll. Remember that the color that we see is the color that gets reflected into our eyes. So when you see the green leaf of a plant, what you are seeing is the green light that's being reflected into your eye. And all the other different colors are the ones that are being absorbed by the chlorophyll. And those different wavelengths of visible light are responsible for the process of photosynthesis. Without the process of photosynthesis, there would be no production of glucose and oxygen. And the glucose and oxygen that plants produce not only sustains plant growth, but it also sustains entire ecosystems. Because if plants did not provide us with glucose and oxygen, there would not be life on Earth. Visible light is used in illumination. This means that we can light our homes, we can light the streets and workspaces, and people can see in the dark thanks to illumination and lighting. Visible light is also used in cameras for photography and videography, and that's because cameras capture visible light to produce images and videos. And we also use visible light in laser pointers. So presentations use laser pointers, which emit this red visible light. In this case, sometimes it is green in a focused beam. The next type of electromagnetic radiation is ultraviolet, also known as UV. And UV waves are an electromagnetic radiation with wavelengths that are shorter than visible light. So that means that UV radiation has a higher energy than visible light. And UV radiation can be divided into 3 types of UV radiation based on wavelength. So we have UVA, UVB, and UVC. UVA rays have the longest wavelength of all UV radiation. It is the most prevalent or the most common type that reaches Earth's surface. Now, UVA rays penetrate the skin and they cause tanning. Now, moderate exposure to UVA triggers the production of melanin. It is a brown pigment that is found in our skin cells. The darker our skin, naturally, the more melanin we have in our skin. And when the sun hits this brown pigment, this melanin, it darkens the melanin and that absorbs UV radiation. It really acts like a shield. The more melanin you have in your skin, the healthier your skin is, meaning the less prone you are to getting skin cancer. So melanin is like a shield. It protects the cell and it prevents the UV radiation from entering the nucleus of the cell where the DNA is and potentially causing DNA damage. Now, overexposure to UV radiation leads to sunburn. It leads to wrinkling, premature aging, and then also the formation of certain skin cancers. When we talk about wrinkling and premature aging, we're really talking about sun damage to the collagen and elastin fibers in the skin. So here we've got collagen and we've got elastin, and those keep the skin nice and elastic. Now, there's nothing we can do about aging, and there's nothing we can do about the fact that with time, the collagen and the elastin will get damaged, but exposure to the sun would speed up this process. Sunscreens contain chemicals that partially block the UV rays. So that means that instead of the UV rays actually penetrating the skin, they get reflected off the skin, and that reduces the risk of sunburn and skin damage. UVB rays have a shorter wavelength than UVA rays. So that means that they have a higher energy. And remember that a higher energy can become more and more damaging. So what we saw so far is when it comes to radio waves have the lowest energy because they have the longest wavelength, followed by microwaves, followed by infrared, visible light, and then UVA. When we get to UVA or UV lights in general, now we get high energy light waves that can start to penetrate our bodies and start damaging DNA. UVA can penetrate skin cells. UVB can also penetrate skin cells. In fact, it has an even higher energy than UVA rays. Now again, UVB is responsible for sunburn, and it can damage the skin's DNA and it can lead to certain skin cancers. Now, luckily, even though UVB is stronger than UVA, only a small fraction of the UVB radiation that's emitted by the sun is going to reach Earth's surface. Most of the UVB radiation gets absorbed by the ozone layer. So here's planet Earth and the surface of planet Earth. And above planet Earth is a layer called the ozone layer. And this ozone layer does allow UVA to penetrate and hit Earth's surface, but it doesn't allow most of the UVB radiation to reach Earth's surface. And we're going to discuss UVC shortly. What we can see is that UVC, which is even higher energy and potentially more damaging, doesn't reach the Earth's surface at all. But this also gives us an idea of why damage to the ozone layer, creating holes in the ozone layer, is so dangerous, not just for humans, but for all living things. Very interestingly is that our body produces vitamin D, and the body uses cholesterol reserves in our bodies along with UVB rays, the few of them that actually reach Earth's surface, and then the body's able to synthesize vitamin D. People that don't get enough sunlight exposure generally need to take vitamin D in tablet form. Vitamin D is essential for the body, and calcium cannot get absorbed properly without vitamin D in the body. So, if you take calcium tablets, you will notice that all calcium tablets also have an extra ingredient in them, which is vitamin D, because there is no point eating calcium if there isn't enough vitamin D in the body to help to absorb that calcium into the body. Excessive exposure of UVB can cause sunburn, wrinkling, aging, and the formation of certain skin cancers. UVC have the shortest wavelength. They are potentially the most dangerous type of UV radiation. UVC is entirely absorbed by the Earth's ozone layer, and luckily it does not reach the surface of the Earth unless there is a hole in the ozone layer. UV light is used in sterilization and disinfection, specifically artificially created UVC light. And when this light is shone onto small living things, unicellular like bacteria and viruses, it immediately damages their DNA and it kills these living things. So we can use these UV lamps in hospitals, labs, butcheries, water treatment plants to disinfect surfaces, air, and water. We also use UV light in security markings, where we use UV ink for security purposes. And that UV ink is then added to currency or identification documents. And under UV light, we can then prove that the currency or that the ID documents are legitimate and authentic, and that prevents counterfeiting, or it prevents fake currency and ID documents from being used. Many animals, including insects, birds, reptiles, and fish, can see UV light, and that helps them to navigate and locate their environment and food. Now, remember that we are blind to the UV light that gets reflected off objects, but like just mentioned, many animals can actually see this UV light. So, for example, bees and butterflies, they use their UV vision to detect patterns on flowers that are invisible to us, but they help to guide these living things towards the nectar. Many bird species also have feathers that reflect UV light, and that makes them brighter or more vibrant to other birds. So we might see a bird like this, but this bird species sees its friends like this. Some reptiles, like geckos and lizards, have UV vision, and that helps them to detect insects that have UV patterns on them. So that helps them to detect their food. Similarly, there are certain species of fish, like salmon and trout, that use UV vision to detect their prey. Furthermore, there's UV light that reflects off the riverbed, and that would help fish species to orientate themselves and to migrate. So it helps them to find their way through the water. The next type of electromagnetic radiation, which has an even higher energy than UV rays, is X-rays. So they have shorter wavelengths than UV light, which means that they have very high energy. Now, because they have such high energy, they can actually penetrate further into the body. So remember that UV rays can penetrate the skin and damage the DNA of the skin, but now X-rays can penetrate even deeper. Their high energy means that they can damage the DNA and they therefore increase the risk of cancer, because by damaging DNA, they actually disrupt cellular processes. They disrupt the processes that happen in cells. The DNA is the brain of the cell. The DNA is the part of the cell that tells it what it needs to do, how it needs to behave. So therefore, precautions are taken to limit exposure to X-rays. We don't want to be overly exposed to X-rays. In medicine, there's often a cost and benefit analysis. So we would only use X-rays when the benefit of using the X-ray is higher than the potential cost of using the X-ray. But when taking X-rays, we apply extra precautions like wearing lead aprons or shields and only using X-rays when absolutely necessary. X-rays are used in medical imaging and CT scans. So X-rays are used in CT scans and they're used in medical diagnostics. It creates images of the inside of the body. X-ray machines send X-rays through the body, and the resulting images will then help doctors diagnose fractures or infections or tumors or some other medical conditions. Now, when we learnt about ultrasound, when we did sound waves, we learned that ultrasound actually reflects off the object. But in the case of X-rays, they don't reflect off the parts of the body that they hit. They actually have so much energy that they pass right through the body. They are then absorbed by different tissues. So here we have an X-ray tube. It releases the X-ray radiation. It moves through the body of the patient, right through, and it creates an image. Now, that's because different tissues will absorb different amounts of the X-ray radiation. So we would then be able to see an image with different colors, like we can see here, depending on how much of this X-ray radiation has been absorbed. Less dense tissue, like muscles and organs, absorb fewer X-rays and they would appear darker, while more dense tissue, like bones, would appear more white. X-rays are also used in cancer treatment. Now, this might sound strange because we said that X-rays can actually increase the probability of a person getting cancer. But that's because they do damage to the DNA. So with cancer treatment, we use X-ray in a very targeted way to damage the DNA of the cancer cells and thereby to destroy those cancer cells. X-rays are used in security screening. So they're used in X-ray scanners in airports and other security settings to inspect luggage and other packages. The X-ray technology helps to identify items in bags that may be hidden or dangerous. X-rays are also used in industrial testing. So what that means is that materials can be inspected using X-rays for defects without actually damaging those materials. So X-rays are used to check the condition of aeroplane parts, concrete structures like buildings, metal beams of bridges, and underground pipes, so that engineers can detect cracks or corrosion or any other structural issues that are not visible to us, but are visible through X-ray radiation. And lastly, we are going to discuss gamma rays. Gamma rays are a type of electromagnetic radiation that has the shortest wavelength and the highest frequency and the highest energy of all the electromagnetic waves. And just note that gamma rays are often represented by this Greek symbol for gamma over here. Now, recall that all electromagnetic radiation is produced at the sun, and that includes from radio waves all the way to X-rays and gamma rays. Remember that most of the UV rays don't penetrate planet Earth because they're absorbed by the ozone layer, and the same thing applies to X-ray and gamma radiation. So most of these damaging light waves don't actually reach us down here. However, gamma rays are not just emitted by the sun. They're also emitted when the nucleus of a large unstable atom, that means that that atom is radioactive, it breaks in order to reach a lower energy state. This reaction releases a large amount of heat energy, and it also releases gamma radiation. So if you consider a very large unstable nucleus here of a uranium atom, it breaks into two smaller nuclei, thereby creating two new elements, and this releases a tremendous amount of energy, including gamma radiation. Because they have such high energy, gamma rays can penetrate many materials, and that includes human tissue. Now, again, remember, UV rays penetrate our skin, and X-rays actually can move right through our bodies, and so can gamma rays. So when absorbed by living organisms, gamma rays can cause significant damage. They can cause damage to the DNA of cells in our body. They can cause cell mutations. They can cause an increased risk of cancer, and they also cause radiation sickness in the shorter term. So that if a person has been exposed to certain doses of gamma radiation due to a radiation leak, say in a nuclear power plant, then it actually starts to create damage of the nervous system, the bone marrow, the digestive tract lining, and a person would then experience symptoms like nausea, vomiting, headache, fatigue, and it is potentially lethal depending on the amount of exposure. But despite their potential harm, gamma rays have some very important and beneficial uses in medicine and industry. Obviously, we have to be careful how we use it. So gamma rays are used in sterilization of medical equipment and food. And that's because they are able to damage DNA. So they are then able to kill viruses and bacteria or anything that might be growing on medical equipment or on food. Foods that have been sterilized with gamma radiation, like spices, herbs, pet food, would be labeled as irradiated. Gamma rays are also used in PET scans. Now, in the case of a PET scan, a patient's given a small amount of radioactive substance that emits gamma rays inside the body, and then these gamma rays are detected by external scanners to show areas of high activity. So, for example, cancer cells are areas of high activity. So gamma rays in PET scans help to diagnose tumors, inflammation, infection, brain injuries, heart problems. In the same way that X-rays are used in CT scans, gamma rays are used in PET scans, and they're both able to help detect cancer. But both of them, X-rays and gamma rays, are also used in cancer treatment. And that is used in radiation therapy, where the cancer cells are targeted with gamma radiation in order to destroy and kill those cancer cells. Gamma rays are also used in nuclear reactors. The way that we make electricity using coal is we burn the coal then heats up water, turns it into steam, and the steam is then able to turn turbines. When it comes to nuclear reactors, we use gamma radiation that is emitted during the radioactive decay of certain materials like uranium atoms. So instead of burning coal, we use radioactive materials like uranium. And when these radioactive materials break up at the nucleus, they release a tremendous amount of heat and energy. And we use that heat and energy to boil water and turn it into steam and turn a turbine. Gamma rays, like X-rays, are used in industrial testing, and it is the same idea. They're used like X-rays to inspect materials and structures for defects without actually having to damage those materials and structures by looking deeper into them. So the radiation alone helps us to detect any damage. This brings us to the end of a very long lesson where we discussed each type of electromagnetic radiation and its uses. In the next lesson, we will learn about electromagnetic radiation acting like a particle as a photon, and then we'll move on to some past paper questions.